Okay, so let's start with that particular question. So what's happening in that is we have some kind of a rod like this, let's say. And the velocities of the endpoints are given to you. So the velocities of the endpoints are given as v and 2v, and they are at angles alpha and beta with respect to the normal to the rod. Okay, so this point, let's say B, it has a velocity of Vb's magnitude is 2v, and this angle with the rod itself is beta. Whereas ये वाले point A का velocity का magnitude V है ऐसा, and the angle that this one is making with the rod, this angle is alpha. Okay. So let's say the center of mass is this point over here. So you can use two concepts here. First of all, what should happen? The approach velocity, the relative approach or separation velocity of B with respect to A, this should be 0. Right, hope this is clear to all of you. So Prayush, I'm unmuting you since this is the question we have sent.
Yeah, sir. So won't the rod rotate about the center of mass, or will it rotate about an ICOR?
Yeah, I've unmuted you, Prayush, but I'm not receiving audio. Okay, I'll try again.
Yes, sir. So I'm asking, will the rod rotate about the center of mass, that point C, or will it rotate about an ICOR?
Hope you guys are able to hear me. Yeah.
Yes, sir. We are able to hear you.
So anyway, hope you guys are able to hear me. Prayush, for whatever reason, I'm not getting the audio from you. So anyway, let's just continue. Okay. So coming back to this question, what is happening here is these velocities are given to us, and we have to check various options. Like we have to check for the relationship between alpha and beta. Then we have to check about the angular velocity of the rod and the speed of the center of mass. So the first concept we can use here is the approach or separation velocity of B with respect to A will be 0. Why? Because it's a rigid rod. Okay. So that means its length is constant. If its length is constant, then A and B cannot be approaching each other. Neither the distance should be increasing nor it should be decreasing. dl by dt is 0. So you can see over here that 2v cos beta minus VA is equal to V in magnitude and VB is equal to 2V in magnitude. So minus VA, which is V cos alpha, should be equal to 0. So that is the first thing that we can say. So this is the relationship between VA and VB, or between cos alpha and cos beta. So you can see that from here you will get cos alpha is equal to 2 times cos beta. This is one thing we will check. Okay. Now the other thing you can always see in a question like this is that the velocity of the center of mass always becomes the velocity of the endpoints, the mean value. Okay. So in this case, what we can do is, for the rod, if I particularly take the axis along the rod as my x-axis and the axis perpendicular to the rod as my y-axis. So if I take this as my y-axis, the center of mass as my origin, it's a moving frame, of course. Okay. Then we'll see that VCM. Okay, now because these endpoints have velocities which are like this, the point over here has a velocity like this at an angle of alpha, and the point over here at a velocity like this at an angle of beta. So we can see that VCM now can be written like this. It has an x component of 0. Not a 0. That will be V cos alpha plus 2V cos beta divided by 2 I cap plus a y component which will be like this. 2V cos beta, sin beta minus V sin alpha divided by 2, because they are in opposite directions, j cap. So this is some kind of Vx that the center of mass is, and some kind of Vy that the center of mass is. Okay. Now, so basically what is happening is that the center of mass here has, let's say, got some kind of velocity like this. Let's just say, suppose the center of mass has some kind of velocity like this, which has a component along this direction as Vx and a component along this direction as Vy. Okay. So what we will see is that with respect to the center of mass, this one's velocity will be like this. This is the velocity of A with respect to center of mass, the relative velocity. And this one's velocity will be like this. Velocity of B with respect to the center of mass. And their magnitudes will be, so suppose it's rotating like this. This one's magnitude, velocity of A with respect to the center of mass, will have a magnitude of omega L by 2. And similarly, velocity of B with respect to the center of mass will also have a magnitude of omega L by 2. In fact, that is why velocity of center of mass becomes this, because you can also see that velocity of A in general becomes VCM plus, if you write this as a vector quantity, it is omega cross R, but R of A with respect to center of mass. Okay. And velocity of B in ground frame becomes VCM plus omega cross R of B with respect to center of mass. Now you can see in my diagram, I've taken the x-axis along the center of mass. So here R of A with respect to center of mass in my particular diagram will become plus L by 2 I cap. And here R of B with respect to center of mass will be minus L by 2 I cap. But in general also, even whatever I take, it will always be such that R of one point with respect to center of mass, one end point, will be minus of R of another end point with respect to center of mass. That's why in this equation what will happen is these two cross product terms will be negative of each other. Okay? So that's why in equation 1 and 2, if you add them, those terms cancel off. Okay? So that's why, so because of that, since omega cross R of A with respect to center of mass, you can see in the diagram also, they are opposite in direction and equal in magnitude, is minus of omega cross R of B with respect to center of mass. Because of this, okay, if you add equations 1 and 2, you get the center of mass velocity equation, which I told you earlier. Equation 1 plus 2 gives you this result, that VCM is the arithmetic mean of VA and VB. Okay. But more importantly, that we have already made use of. Okay. But also, if you subtract the two equations, you will get VA minus VB is equal to omega cross R of A with respect to center of mass minus R of B with respect to center of mass. So you get this very nice equation that VA minus VB, this relative velocity of between A and B, is omega cross R of A with respect to B. Like this. Okay. So you can also do this over. Okay. Now when you do VA minus VB, obviously this VA minus VB will not have a X component. Okay. This one's X component in my diagram will be 0 because approach velocity or separation velocity of A with respect to B has to be 0. So this will only have a Y component. Okay. This will not have an X component. This will be perpendicular to the rod itself. Okay, and that is why you can see that will be coming back in this diagram. क्या होगा कि ये जो दोनों velocities है VA and VB, इनके components along the rod same है. That is what we've seen earlier also, that V cos alpha is equal to 2V cos beta. So that term cancels off when you subtract, but the other term, the perpendicular component, that actually adds when you subtract. तो इसका perpendicular component कितना है? V sin alpha clockwise, और इसका भी 2V sin beta. So when you subtract those, this term that you will get, that VA minus VB actually that you will get. My diagram, you can see that it will become sin alpha plus 2V sin beta along the minus j cap direction. Just reference it to the diagram and you will understand why it is along the minus j cap direction. I have taken this as my y-axis. So this is the negative y-axis. Like that. So this should be omega, which I have taken clockwise. So omega is like that, cross this thing. So on the other side of the equation, I should have omega, which is nothing but omega minus k cap as a vector. Cross product with this thing. So E is position with respect to B in my diagram, you can see is L I cap. So again, you can see directions are also matching. This is along minus j cap, and minus of k cross I will give you minus j. So you will get this relation that V sin alpha plus 2V sin beta. Okay, this thing which is along minus j cap should over here be omega L into this thing which is along minus of k cap cross I cap. So your unit vector is also taking care of itself, but more importantly, omega is becoming this term. It is becoming V into sin alpha plus 2 sin beta divided by L. So this becomes the relationship that you are getting between omega and this. Okay. So this is your omega. Okay. Then of course your VCM we have already written. Let's say this is the third. Okay. VCM I have already shown you here as this. Okay. And also the constraint relation. This one. This is the relationship that you are getting from the constraint. So this is the complete solution of this. So I'm just minimizing this so that people can have a look at this together, each of the parts, and then I'll share the next question that I'm solving.
Sir, I had sent you a question. Did you receive that?
When the final result where you are calculating omega in terms of all that, you will also have to use this relation that cos alpha is 2 times cos beta. So You have to eliminate some term using that over there. So, do that.
Sir, I had sent you a question. Did you receive that?
Okay, so you have equation 1, which I hope all of you understood. Then this other equation that I've written, that VCM is equal to VA plus VB by 2. You should always know this as a fact actually. Whenever we have a rigid body, okay, such that you are considering 2 points, any 2 points which are diametrically opposite to the center of mass and equidistant. अगर कोई भी 2 points ऐसे हैं that this distance is equal to this distance, and it is basically such that r of A with respect to center of mass is equal to minus of r of B with respect to center of mass. अगर ऐसा है, then it automatically implies that velocity of the center of mass becomes VA plus VB by 2, and also omega about the center of mass will become that VA minus VB divided by 2x. These two equations will hold true. Why? Because this will hold true. Because this equation 1 and equation 2 will hold true. This is a general equation, but here the moment we have this condition that r of A with respect to center of mass is minus of r of B with respect to center of mass. So whenever that happens, this term over here, this omega cross r for A and omega cross r for B, they are equal and opposite. So that is why if you add these two equations, you get the VCM wala equation, and if you subtract these two equations, you get the omega wala equation, and this is the relationship. Okay. So using this, we have got omega over here, and in the final equation for omega, I think you have to eliminate one of the two terms, sine alpha or sine beta, and sine beta. Okay, so I think with this, it should be clear. Okay, so I'll go back to sharing the next question now. So again, I'm starting with the lot that Prayush has sent. So this is the next question. So just go through the question and I'll explain again. Okay, so to analyze this question, what it's basically talking about is you compare a circular orbit of a satellite with another orbit of a satellite which is elliptical like this, let's say, and another one which is elliptical like this, such that the diameter of the circular orbit is equal to the semi-major axis of the other two orbits. Okay. So इस वाले का जो diameter है, इस वाले के semi-major axis के बराबर है. I mean, radius is equal to semi-major axis. और इसका, let's say this one star is over here and the planet is orbiting like this. And let's say for this one, there's this And for this one, the star is somewhere here. The planet is orbiting like this. And this one, of course, it's a circular orbit. So the star is at the center, is the common focal point, you can say like that also. Okay. So now we have to compare what all things. We have to compare, I think, angular momenta, energies, and things like this. So we have to compare orbital energy, angular momentum of the planet around the star. Okay, that's it. These two things we have to compare. So let's say this is case 1, this is case 2, and this is case 3. Okay, so this should be a fairly standard type of question. You just try it out. I'll give you a hint of what all you have to use. Okay. You have to use basically Kepler's laws and understand how Kepler's laws also applies to a circular orbit. So for circular orbit, remember you have this relationship that the orbital energy is equal to minus gmm upon 2 times r, or negative of the kinetic energy, or half of the potential energy for circular orbit. And we of course have orbital speed is square root of 2 gm upon r. Okay. Here r is not the radius of the planet or something. Okay. R is the radius of the orbit. R is orbital radius. What for satellites you write as the radius of the planet plus the height at which the satellite. That is what. Okay. And time period, which is 2 pi r upon VO. Therefore, the time period becomes 2 pi r to the power 3 by 2 upon square root of 2 g. So this is the relationship between time period and this. This is the relationship of energy. Okay. And therefore your angular velocity, which is 2 pi by omega, or v orbital by r. So you can see your omega is equal to or we can also do like this. We can directly look at the angular momentum. That will be easier. So this will become square root of 2g capital M small m cube, okay, into r to the power half. Oh, sorry, m square, not m cube. So basically, angular momentum is proportional to root of r. V is proportional to square root of 1 by r, like that. So this is about the circular orbit. Now about the elliptical orbit, similarly, what equations we have? Time period is proportional to semi-major axis to the power p by 2. Okay. And there also the relationship is that only, that time period is equal to 2 pi upon square root
So how do we solve for the second option?
2 gm into semi-major axis to the power p by 2. That is what we can say about time period. Okay. Now, what we can say about energy. and this thing in terms of semi-major axis in this thing, what we can say about energy. And so if you compare the aphelion and perihelion, those points, the minimum distance and maximum distance point. Suppose the star is present here. Now, when the planet is at this point, it is having maximum velocity and minimum distance. And when it is at this point, it is having minimum velocity and maximum distance. So you can see that V minimum into R maximum is equal to V maximum into R minimum. Okay. And you can write this R maximum in terms of eccentricity also. Okay. So what we can do here is write this as A into 1 plus E. And similarly on the other side, R minimum is A into 1 minus E. We can make use of this as another equation. So angular momentum conservation and energy conservation. So finally, you can understand the relationship between time period and age. So that will be there. Now it is a matter of eliminating your this thing, V max and V minimum. So you have that relation that half mv max square.
Sir, what is E here?
Minus gmm upon R minimum is equal to half mv. V minimum square okay. So if you compare this relation now, you have half of V max square minus V minimum square is equal to Gm 1 upon R minimum minus 1 upon R max. You have a relationship like this also. So this is like another equation.
Sir, what is E in the first equation?
So some kind of comparison will have to be done here of these, where you express R max and R minimum in terms of eccentricity. So you will see from here, you will be able to understand that the ratio of V max, so from equation 1, you can see that ratio of V max to V minimum, how it depends on eccentricity. It is 1 plus E upon 1 minus E.
Okay.
And here also, in equation 2 also, you will substitute R max and R minimum's inverse ka ratio, ka difference in terms of eccentricity. So from that, you will kind of get an idea about how eccentricity affects this whole relationship.
Okay.
And from that, you should get an idea of the energy and angular momentum. So just give it a go over here. Try to understand that from these relations, how we'll be able to relate that in the above diagram, which of the two elliptical motions has more energy or less energy, or more angular momentum or less angular momentum. Yeah, Prayush, to answer your question, that rod over there in the previous question, it is in general rigid body motion. So it is in a combination of translation and rotation. So that's why. Yeah, and Dhruv, to answer your question, I have received your question on WhatsApp. So I will be taking it up soon. Okay.
But I have also sent.
Okay,
Okay,
sir.
so now on the basis of this, what can we say about angular momentum and energy in terms of eccentricity? So, for example, if this on this side, this will become
बहुत गंदा टेस्ट था इसका ऑरिगेनो लगा हुआ था इसके ऊपर मीठे बिस्किट के ऊपर
ऐसा हो जाएगा इसमें।
नहीं मीठा बिस्किट है ना ये नसीब वाला अब बोलो दो चीजें आपके
So 1 minus e whole square minus of 1 plus e whole square. Oh, sorry, this is reverse. No? V max is, so my mistake here. This should get inverted. Okay. So ये कितना हो जाएगा 4e upon 1 plus e whole square is equal to so V max becomes something like the square root of this 2 comes there, so 2 also cancels, so square root of gm upon a into this kind of a term. E is cancelled in the numerator 1 plus e whole square. Okay, so Understood? So angular momentum now is mv max into r minimum. So that is m into this quantity, small m, that is, into square root of g capital M upon E into this factor 1 plus E upon 1 minus E into R minimum. Now R minimum was A into 1 minus E. So you can see that the angular momentum is now like this. It is, take all this terms inside the square root. So we'll have capital G M small m square E into this factor into 1 minus E ka whole square. So that it will become 1 minus E square. So this is the relation of angular momentum with eccentricity. So this is, let's say, our equation 1. And similarly, our total energy, which we can write as half m v max square minus gmm upon r minimum. This also we can write in terms of eccentricity, because now we've got v max and this thing both in terms of eccentricity. So our total energy is half m. So v max square you just substitute from here. So capital Gm upon E into 1 plus E upon 1 minus E. So ये मेरा maximum kinetic energy हो गया, which is clubbed together with the minimum potential energy. So again you have that kind of term. You can take Gm upon E into 1 minus E, in fact, as the common denominator. So you will have 1 plus E by 2 from here, okay, and minus 1 from here. So the energy becomes actually, it's a negative quantity, so I'll write it this way. Okay. This will become 1 minus.
So small m is also there.
The relationship of energy with eccentricity is nothing. It just depends on the semi-major axis. So these are your relations for elliptical orbit now. So I'm just minimizing this. Okay. Now, these are not equations that we study as standard equations. So that's why this question has become very lengthy. If you've studied these at some stage as standard equations from higher physics, then you could have answered it directly. But I'm just showing you how the derivation is done for this. Okay. So just go through this elliptical orbit thing once. And tell me if it is okay. Ask me if there's any doubt or any confusion.
Sir,
Then we'll come to the next question.
Sir, you have missed the small m.
Small m is missing. This is okay, dimensional.
Sir, last step.
This is also okay, dimensional. In this small m. Correct. Yeah, so friends, I don't think you have to remember these equations or anything. Okay. Anyway, this question is done. Okay, now I'm moving on to another question set. Okay, just hang on. Okay, so next I will share one of the questions from Kritika. Okay, so let's look at this particular question. This, I think, is a question that most of you should be able to solve. So just try it out as a practice question. All right, so got the question. So let me explain it. Just give me a second. Okay, so let's come to that lenses question. So what the question is saying is that we have two identical glass lenses of focal length f each, which are kept in contact, and the space between the two lenses is filled with water. So the focal length of the combination becomes what? So the thing is that it's not even telling you whether they are converging lenses or diverging lenses, but they are equiconvex lenses. So it is converging lenses. So the fact is that when refractive index of glass is equal to 3/2 and you have equiconvex lenses of focal length f, then what happens? The radius of each side becomes equal to f. The magnitude of the radius of each side, it actually becomes equal to f. And this is quite easy to understand because using the Cartesian sign convention, if you follow this, light coming from this side, this is where your first center of curvature is, this is where your second center of curvature is. So if you use the formula with this side negative, this side positive, you will see that 1 upon plus f will become mu2 minus, mu of glass minus 1 into 1 upon r1, which will be plus r, minus 1 upon r2, which will be minus r. So the focal length has the same magnitude as the magnitude of radius. Okay. Substitute this distance as r and this distance as r because they are equiconvex. So r1 should be substituted as plus r and r2 should be substituted as minus r. So ये करके over here in the lens maker's formula you get this relation that the magnitude of each side's radius is equal to the focal length. Okay. So now what is happening is in this particular question you are doing this. You have these two symmetric biconvex lenses which are kept in contact. Let's say they're like this, actually in contact, and in between there is water, let's say. So now you use the lens in contact combination formula. Okay, so you have lens 1, let's say, lens 2, let's say, and lens 3. So so f1 is equal to plus f, which we got earlier. f3 is also equal to plus f. Okay, but f2, which is a water lens, is focal length you have to find out. So for the water lens's focal length, you again make use of the lens maker's formula. So mu of water is 4/3, and for light coming from this side now, using the standard convention, here also light is coming from this side, and this side is negative, this side is positive. So we will take R1 as minus R and R2 as plus R. So our lens maker's formula will tell us that 1 upon focal length of the water lens is 4/3 minus 1 into 1 by R1 minus 1 by R2. So F2 with proper sign becomes minus 3/8 R, or that is minus 3/8 F. This is for the water lens. Now the combination will have an equivalent focal length, which will be this. The equivalent power is the sum of the powers. Use that. Okay. So this is glass lens, water lens, again glass lens. So this will become 1 upon F plus 1 upon minus, how how much was it? 3 by 8. 3f by 8 plus 1 by f. You take 1 by f common, you have 1 minus 8 by 3 plus 4. Oh, sorry, there's a mistake here. That's what I thought. The glass should give you much less power. How can it give you 8 by 3? So this is so 2 minus 2 by 3 will give us 2 we can take common, 1 minus 1 by 3, 4 by 3. So 1 upon equivalent focal length. So the equivalent focal length is plus of 3 by 4f, which means that the combination acts like a converging lens. Of f equivalent 3f. Okay. So hope this is clear. Okay.
Sir, please discuss my question.
Okay, good. Now I'm sharing one more question from Kritika, then I'll come to Dhruv's questions. But before that, if just minimizing this for you for a moment, so you can go through the whole thing. But I think this is fairly standard. You should know this. And it's very useful to just keep this fact in mind directly. That जब भी 3 by 2 होता है glass का refractive index and it's symmetric, because this factor here becomes half. You can keep in mind this thing. Whether it's a symmetric biconvex or biconcave, जैसा भी हो, but symmetric है and mu is 3 by 2, then the magnitude of the radius is always equal to the magnitude of the focal length. Because many questions are based on this. So you should remember these basic simple little facts. Okay, next, coming to this question, which is heat and thermodynamics. So go through this question and try to work it out. I'll discuss. So monoatomic gas helium, adiabatic compression. So use that relationship. So you have to just basically find out the expression of work done for adiabatic process. Work done will be negative of change in internal energy. And generally they should specify whether they are talking about work done on the gas or by the gas. But here, either case, everything is given with as a modulus. So just take it that way. Because it's compressed, no? So that means work is done on the gas. So if you are expressing work as a positive quantity, you are talking about work done on the gas. If you are talking about work done by the gas, it should be negative in the compression. So you can see the volume is becoming 1/8. So the temperature will become how much you can calculate. Okay, so hope you worked out this question by now, people. So in case you haven't, I'm just giving you the basic working for it. So in this you are having a monoatomic gas. Okay. So gamma is equal to helium gas. So 5/3. It is undergoing 5.6 liter to 0.7 liter to a adiabatic compression, and initial temperature is T1. Number of moles भी आपको दिया हुआ है. So n is equal to 1. Okay. So for adiabatic process, you know that your W plus delta U is 0. So work done by the gas, that is negative of delta U. So it is minus of N F by 2R delta T, which you can also write as, now you can write the relation between so 3 by 2 delta T हो जाएगा, ठीक है, where this is work done by the gas. And the question they have obviously talked about work done on the gas because it's given as a modulus, because n is equal to 1 and all that, and degrees of freedom is 3. Now delta T कैसे निकालेंगे? We'll just use the relation PV to the power gamma is constant, so that means PV to the power gamma minus 1 is constant. So T1 V1 to the power 2 by 3 is equal to T2 V2 to the power 2 by 3, because gamma was 5 by 3. So your T2 will become T1 into V1 by V2 to the power 2 by 3. So that is T1 into 5.6 divided by 0.7 to the power 2 by 3. So that is T1 into 8 to the power 2 by 3. So that is T1 into 2 square of 4T1. So T2 is equal to 4T1, just substitute that here. So work done is becoming by the gas, that is becoming minus 3 by 2 into T2, which is 4T1 minus T1. So they should become minus 9 by 2 T1. That is work done by the gas, and you can just calculate the magnitude of that. That will become it. So as I said, fairly straightforward question. So now let me come to a question sent by Dhruv also. All right, so this should be clear, I think. Nothing very difficult here. It's the standard equation of adiabatic process. But then that is what you expect at mains level questions also. Okay. Next up, we'll discuss this question sent by Dhruv. Okay, so just go through this and I'll explain. So it says a semicircular glass tube filled with water containing an air bubble is shown in the diagram. Filled with water and it is sealed at both ends. So that semicircular tube has water, it's sealed at both ends. It has an air bubble inside it, which is at that angular position theta with the vertical. So if the tube is held in a vertical plane and made to move in the plane with constant acceleration, and while it is moving with this constant acceleration, the bubble is in equilibrium, or remains at rest with respect to the tube at that angular position theta shown. So from that, what can we conclude about the acceleration vector of the tube? So you have to find the magnitude and direction of the acceleration vector of the tube given. So this has to do with pseudo force. Okay, so this question will be handled by understanding pseudo force. So just make the diagram and make the FBD of that air bubble, which is shown at that angular position theta. So make that air bubble of that at that angular position theta. Make its free body diagram. In the non-inertial frame of the this thing of the tube, and from that we should be able to figure out what is the direction of pseudo force acting on. So the forces acting on that air bubble will be weight, pseudo force, and buoyant force. But remember that in an accelerated frame, the pressure gradient also has another component because of the acceleration. Remember the case of the horizontal accelerated tank and all that. So pressure gradient had a vertical gradient and a horizontal gradient when there is horizontal acceleration. So buoyancy also has two components then, vertical and horizontal, if you're talking about a horizontal acceleration frame. So the total number of forces acting will be 3 only. Okay, but the buoyancy will have two components in case you're talking about horizontal acceleration. Okay, so I'll just make the FBD for you. Okay, so let's say a semicircular tube is something like this. So it's sealed. Now at some angular position theta like this, our air bubble is at rest in the non-inertial frame, which is having some kind of acceleration, which I don't know. So if I assume, or let's first talk about the forces other than this thing. This is a vertical plane. So other than this thing, your forces would be weight, would have to be balanced by buoyant force would obviously be greater than weight, because buoyant force would be density of water into volume of the bubble, let's say delta V into G, whereas mg would be density of air into delta V into G. So you can see here that basically your mg is negligible in comparison. So mg is actually a much smaller vector. So mg is probably, you can neglect mg altogether even. So anyway, so this kind of situation would tend to make the bubble, accelerate like this tangentially, because buoyancy has a component like this. So that means there must be some kind of pseudo force is helping us. So that means, and again, that pseudo force will have to be buoyancy. Yeah, normal reaction will also be there. Okay. But I'm just saying, normal reaction will not affect the tangential motion. So at the moment now, what is happening is, along with these two, there is also force because of the acceleration of the frame, and that force should be such that buoyancy's horizontal component should be like this, and the pseudo force itself acting on the bubble should be like this. So ये buoyancy का x component हो जाएगा और ये pseudo force हो जाएगा. And this is buoyancy's y component. Okay. So what happens here is, you have to keep this in mind, that if you have a body of liquid which is, for example, accelerated like this. Okay. So in this, if you have a system of coordinates which are x and y like this, and of course gravity is acting like this. So in a situation like this, what happens is, your pressure's vertical gradient is minus density of the fluid into G, but your pressure's horizontal coordinate component becomes, or rather horizontal gradient becomes like this. Okay. So as a result of that, in a liquid like this, if you have any body like this, it experiences vertical component of buoyancy like this and horizontal component of buoyancy like this. So the vertical component of buoyancy becomes density of fluid into volume of the submerged part into G, and it acts against gravity, opposite gravity. So this acts
The pseudo force is acting towards left.
opposite gravity. And your horizontal component of pseudo force, or buoyancy rather, not pseudo force, is density of fluid into volume of submerged part into A, and this acts opposite pseudo force. Okay. So in other words, it acts along the external acceleration. Along the acceleration. Okay. So that is why. So if my pseudo force is towards the left and bx is towards the right, that means my non-inertial frame is actually having an acceleration in this direction. And that is why bx, the buoyancy's x component, this is the y component, into volume of the bubble into E, and this will act along the acceleration vector, whereas pseudo force with density of air, this will act like this. So the condition for equilibrium actually becomes like this. The condition for equilibrium becomes buoyancy's vertical component minus mg. So that's along this direction. So its component along the tangent will become sine theta. Should be balanced by buoyancy's x component minus pseudo force. That is a net force towards the positive x-axis. That's one component along the tangent, which is positive. So you will see that this is actually density of water minus density of air into volume of the bubble, delta V, let's say, into G. That should become again same thing, density of water minus density of air. Into delta V into E cos theta. So the important thing here is E equal to G tan theta. And the positive x-axis in our standard coordinates. We take our x-axis like this and our y-axis like this. So because A is along the positive x-axis, that is why a pseudo force is along minus I cap, and of course gravity is along minus j cap, and that is why your buoyant force's x component is along plus I cap, because it opposes pseudo force, and your buoyant force's y component is along plus j cap because it opposes gravity. So this is a very important general concept in a question like this. So let's go through this. So this was the previous question. So alright, so just before you go through this and discuss the next, I'll share the next question also. Okay, so we will hope this is clear fully. Now I'll share the next question. This is a question which is somewhat more complicated to do with thermodynamics. Okay, so just go through this question first and try and understand the whole thing about the question. Okay. So just go through the question, make that graph on a piece of paper because we'll be using that. Okay. And try and understand the question first, I'll explain. Okay, so what all is given to us is given that in the situation we have a cube, solid cube of aluminium. Density of all aluminium is given, molar mass is given, so you know the total mass of aluminium that you have because you know volume and all this. Now the heat capacity of aluminium is actually varying with temperature. Okay, and the heat capacity is given in terms of molar specific heat capacity. So you can calculate the number of moles of aluminium within the cube and all that because density, molar mass is given to you, density is given to you and all that. Okay. Now speed of light is also given to us and gas constant R is given to us and Cv is given in terms of temperature. Okay, like this. Okay. Now the cube has 5 faces painted in white which reflect all wavelengths and one face painted in black which absorbs all these waves. Okay. And the cube is surrounded by vacuum at very low temperature near absolute zero, so there's no gravity also. Initially the cube is at rest and it cools down due to radiation, and as it cools it starts to move slowly. Okay, so you have to find the final temperature assuming that the radiation emitted by the cube is normal to its surface. So basically, you know, this is kind of related to the concept of radiation pressure. Okay, that is, assume that, you know, in a reflecting surface your photons are making perfectly elastic collisions. If they reflect back, any photons that reflect from a perfectly reflecting surface, so photons have momentum h by lambda. So because they bounce back or reflect back into the same medium from which they were incident, so they are having the same wavelength. So photon coming and making a normal incidence at a momentum of h by lambda bounces back with a momentum of minus h by lambda. Or suppose it makes at an angle of incidence theta, then you will have to take the normal component. So it will become h by lambda cos theta. So that component gets reversed. So by that you apply impulse momentum concept. From impulse momentum concept you get rate of change of momentum, and from that you try and understand what is happening. So fairly complicated question. Number of things you have to keep track of over here. Just try it out. Okay, so hope you have tried this question out so far. So I'll explain how this works. So we have a cubical box which has all this considerations given to us. The side length of the cube is 1 centimeter. So the volume is 1 centimeter cube or 10 raised power minus 6 meter cube. Is made of solid aluminium, and the density of aluminium is given to us as 2.7 gram per cc. So the mass of aluminium that we'll have is 2.7 grams or 2.7 into 10 raised power minus 3 kilograms. Okay. And also given to us that the molar mass of aluminium is 23 grams per mole. So we have number of moles here as 2.7 by 23. So we have fractional amount of moles in it. Okay. Now it is given that 5 faces are painted white and they reflect all wavelengths. So suppose, and one is painted black, which does not reflect. So let's say this one is the black one. So this is the black face, and the other 5 faces are all white faces, which are 100% reflecting. And outside the temperature is tending to 0, okay, and is vacuum. Inside the temperature is initially 300 Kelvin. Okay. And we are assuming that what is happening is that as it cools down due to radiation, it starts moving very slowly. So you have to find its terminal speed. Okay. So if we kind of take a side view of this, okay. Now suppose in that side view, this is the black face and this side is the white face. And obviously this is also white. This other 5 faces are also. So we have, and this is the single black face. So you'll understand that photons that are bouncing back from here, okay. So we assume there is radiation happening over here. So photons which are bouncing back from here are applying some kind of net force on this, which is, let's say, F1, and photons which are being absorbed here are applying some net force F2. F1 will be greater than F2 because there is more momentum transfer happening when there is reflection, less momentum transfer happening when there is no reflection. Okay, so to understand that, if you have a reflecting surface and a photon of wavelength lambda comes and bounces off like this at an angle of incidence theta. So what happens is that the impulse or the change in momentum which acts on the surface because of this. So when this comes and hits here, the surface applies an impulse like this. So the surface experiences an equal and opposite impulse like that. So that impulse is equal to how much? It is 2 times h by lambda cos theta in the case of reflection. Whereas in the case of absorption, it doesn't reflect. So that impulse just becomes, the normal component of impulse becomes this much. Okay. So that is why you can see that there is more force in this compared to this. Okay. All right. So now we have to just understand that on this surface of dimension L by L, the emissive, or let's say absorptive power, or you can think of it like this, that the energy incident per unit time dq by dt will be equal to sigma into L square into the temperature to the power 4. Okay. So this is energy per unit. So you can say photon flux, say n, that is number of photons incident per unit time on that surface, and that will become energy incident per unit time divided by energy of a photon. That is assuming if there was monochromatic light of wavelength lambda only. Now here, of course, there is the entire spectrum, but that factor of lambda will get cancelled out when we talk about momentum transfer. Okay, so that is why I'm not keeping that over here. So lambda upon hc into sigma into L square into t to the power 4. This is the photon flux. Okay, so now if I write J as the impulse per photon reflected. Okay. Now see what is happening. A photon in general will have a momentum like this, which will have a magnitude of h by lambda. So if we take 3 mutually perpendicular axes and again go by that random motion kind of theory that is applicable like Brownian motion for ideal gas, you will see that px का mean value, so px square का mean value का square root, so that is like an RMS value, root mean square value of the x component of momentum, that will become how much? H by lambda into 1 by root 3, that kind of fact. Okay, so this J let's assume the wall we are talking about is the YZ plane. So this J should be equal to 2 times Px. So the RMS value of J, the average per mole per photon, will become 2 times h by root 3 lambda. Okay. So now the average force should become photon flux into average momentum transferred or average impulse per photon. So this was dq by dt divided by hc by lambda, and this was 2 times h by lambda by root 3. So that is why your lambda factor doesn't matter. So the average force becomes like this. It becomes 2 by root 3. H by lambda cancels out, and we have dq by dt divided by speed of light. So it should be something like this: 2 by root 3 into sigma into surface area into temperature to the power 4. This is like the average force. So coming back to our original diagram, what was happening is, if you see the side view, there is a force on this side because of reflection, and there's a force on this side because of absorption. So this F1 will be this factor only. It will be 2 by root 3 C sigma L squared T to the power 4. Whereas this F2 will be half of F1 because there's absorption happening over there. So the average impulse per photon incident is half. Okay, so it's becoming 1 by root 3 C sigma L square into T to the power 4. So from this you are seeing that the net force that is acting that should depend on temperature this way. Okay. So the net force is F1 minus F2, and that becomes temperature dependent. Okay. So as the temperature starts decreasing, the net force also starts decreasing. Okay. Now initially the walls of the container were at absolute zero. So this was about the net amount of photons absorbed and all that. But as the as the body starts heating up, or rather as the body starts cooling down, the loss of heat is converted into kinetic energy. Okay, so hope this is clear up to this step. Now people, actually, unfortunately, I will have to finish the session here today because I have another session coming up and at 11 o'clock, and I also have to kind of, there is a package I have to collect in between that. So I will send you the remaining part of this and the other doubts I'll try to clear by WhatsApp till we have our next doubt session. Okay, so that's it for today's session. I'll send you the recording and the whiteboard sheet of this also. Okay. Now this question has a little bit more analysis we have to do still, so I'll help you with that. So the analysis will be a combination of this concept of net force and also the concept that the heat loss results in kinetic energy. But my only problem with the question right now is that if you have to consider heat loss and you are given that graph, between CV and temperature, then to consider the heat loss in this graph, you will actually need to calculate this area. Now there's no equation given for CV. So how will we calculate the area? So maybe it is one of those questions where, the graph is given exactly in terms of boxes and all that. So we have to actually sit and count the boxes and try to geometrically calculate the area under the curve. And from that, I don't know, maybe it is something like that. Okay. Right. Yeah, I'll send this question on the group. Don't worry. Okay. So unfortunately, because of some time constraint, I'm not going to be able to finish this over here. I will send the solution in the whiteboard later, which I sent. Okay. So that's it for today's session, people. And the remaining doubts and any other doubts that you have, you can keep sending me on WhatsApp or until the next session that we have. Next session will probably be again next week. So I mean, okay.